Hey everyone, and welcome. Now, if you're an engineer or a data practitioner, you already know our entire world pretty much runs on numbers. But what happens when your data isn't numbers? What if it's language? You know, the messy, beautiful, complicated thing we use to talk, to argue, to create. Well, that's exactly what we're going to tackle today. We are going on a quest for meaningful numbers, taking a deep dive into the fundamental techniques that let our machines finally start to process and even understand human language.
So let's just jump right in with the most basic question of all. Why can't a machine just, well, read? The answer seems simple, but it's actually really profound. You see, our machine learning models, our deep learning models, for all their incredible power, they don't speak English, or any human language for that matter. They speak the language of math. They run on numerical data, vectors, matrices, you name it. A raw piece of text, a string of characters like hello world, is totally foreign to them. And that creates this huge gap that we as engineers have to figure out how to bridge. And the bridge we build to cross that gap? It's called feature engineering. This is, without a doubt, one of the most critical pre-processing steps in any ML project. It's where we pull out or engineer meaningful features from raw data. Now, for some things, like images or audio, this is kind of straightforward. An image is already a grid of pixel values, right? And a sound is a waveform. They both have a mathematical structure built right in. But text? Oh, text is a whole different beast. It's often a much more creative and, frankly, more challenging process to turn that raw, unstructured text into a numeric form that a model can actually learn something from.
So, when I say feature, what do I actually mean? Well, think of a feature as just an attribute, some kind of measurable property that's useful for whatever problem you're trying to solve. In the machine learning world, if you just picture your data as a giant spreadsheet, the features are just the columns. That's it. So our whole goal here is to take a big, messy pile of text documents and turn it into a clean, structured table of features. A table where every row is a document and every column is a number that captures some piece of what that document is all about.
So here's our roadmap for today's journey. We're going to start with the core problem itself. Then we'll look at the simplest possible solution, just slapping some numbers on things. After that, we'll dive into the classic bag of words model and then a smarter way of counting called TF-IDF. And we'll wrap it all up by talking about how you actually choose the right strategy for your project, looking at all the trade-offs along the way. All right, let's get into it. Section 1. As we've said, the absolute core of the challenge is turning text into vectors of numbers. This is the bedrock of pretty much all of natural language processing.
And the big idea that makes all of this possible is something called the vector space model, or VSM. Now, don't let the name intimidate you. It's a really simple but incredibly powerful idea. We represent our text, words, sentences, whole documents, as vectors in a high-dimensional space. Just imagine that every unique word in your vocabulary is its own dimension on a giant map. Once we plot our text on this map, we can suddenly use all the tools of mathematics, like geometry and algebra, to measure relationships, to find similarities, and to uncover all these hidden patterns inside the language itself. It's pretty cool. And one of the most common tools we use on this map is cosine similarity. This is where things get really interesting, because it lets us put a number on meaning. Now, instead of measuring the distance between 2 points, we measure the angle between their vectors. Why? Because the angle tells us about their direction, their orientation. Think about it. 2 vectors pointing in the exact same direction have an angle of 0 degrees, and the cosine of 0 is 1. That means they're a perfect match, super similar. But if they're pointing in complete opposite directions, that's an angle of 180 degrees, and the cosine is -1. Totally dissimilar. This is how a VSM can figure out that 2 sentences are talking about the same thing, even if they don't use the exact same words.
All right, now that we have that foundation, let's see how it plays out in our very first attempt at this. We're going to start with the most intuitive, most straightforward approach you could possibly think of. We're just going to assign a number to every word. But wait, before we do that, we have to talk about a super important distinction in data types: nominal versus ordinal data. Now, nominal data is just categories with no natural order. Think red, green, blue. None of them are more or less than the others, they're just different. Same with male and female. Ordinal data, on the other hand, has a very clear logical sequence. Small, medium, large. There's an obvious progression there. Or a sentiment, like unhappy, neutral, happy. This difference is absolutely critical because getting it wrong is the #1 mistake, the fatal flaw in our very first technique. And that first technique is called label encoding. It is exactly what it sounds like. It's a really simple method where you just convert your categories into numbers by giving each one a unique integer. So red becomes 0, green becomes 1, and blue becomes 2. Easy enough, right? Maybe a little too easy. So how does it actually work? Well, it's basically a 4-step dance. First, you clean up your text. You know, the usual tokenizing, lowercasing, all that stuff. Then you build a master list, a vocabulary, of every unique word you've got. Third, you go down that list and assign a number to each word. And finally, you just go back to your original text and swap out the words for their shiny new numbers. A sentence becomes a simple sequence of integers.
Let's make this real with an example. So here we've got Asia mapped to 1, capital to 2, and India way down at 6. So if we had a sentence like India country occupies, that would just get turned into the vector 6, 3, 8. It looks like it's working perfectly, but there is a very dangerous trap hidden here.
So let me ask you, what is that hidden danger? Imagine for a second we're encoding customer sentiment. We decide, okay, happy is 1, neutral is 2, and unhappy is 3. To us, those are just labels. But to our algorithm, to our mathematical model, it just sees numbers. And it might start to learn that unhappy, which is 3, is somehow 3 times more impactful than happy, which is 1. Or it might assume that the distance between happy and neutral is exactly the same as the distance between neutral and unhappy. It's learning a mathematical relationship, a false priority, that just doesn't exist in the real world.
So here's the bottom line. Label encoding, it's super simple to do, and it's very efficient with space. But its limitations are massive. Its fatal flaw is that it creates a totally fake ordinal relationship on data that has no natural order. And that can trick your model into learning patterns that are just complete nonsense, all because of the random numbers we picked. And of course, it also throws away all information about word position and context. So for all these reasons, label encoding is usually a really bad choice for representing features.
So that leads us to a really important question. If just assigning one number creates this false order, how do we represent these categories in a way that doesn't imply any kind of relationship? How do we tell the model that red, green, and blue are just different? And the answer to that is one-hot encoding, or OHE. And this technique, folks, is a brilliant fix for that ordinality problem. Instead of using a single number, OHE represents each category as a binary vector, a list of zeros and ones. Just picture a giant switchboard with one light switch for every single word in your vocabulary. To represent a word, you find its switch, you flip it to on, that's a 1, and you make absolutely sure every other switch is off, all zeros. Only one light can be hot at a time.
Let's look at a simple example. Say we have one categorical feature, city, and it has 3 possible values, Mumbai, Delhi, and Bangalore. With one-hot encoding, we create 3 new columns, C1, C2, and C3. Mumbai is now represented by the vector 1, 0, 0. Delhi gets 0, 1, 0, and Bangalore is 0, 0, 1. See what happened there? We've totally removed any sense of order. The model can no longer assume that one city is greater or less than another. They are all equally different.
Okay, so let's check back in. Remember that whole false priority problem we had with label encoding? Well, one-hot encoding just completely solved it, which is a huge win. But, as with any engineering decision, there's no such thing as a free lunch. This beautiful, elegant solution comes at a price. It introduces a whole new set of challenges that we now have to deal with.
The biggest price we pay is something called sparsity and high dimensionality. Think back to that switchboard. If your vocabulary has, say, 50,000 words, that means every single word is now a vector that's 50,000 numbers long, with 49,999 zeros and just one little 1. These are called sparse vectors, and they are a real pain. They eat up a ton of memory and can be really slow to work with. On top of that, OHE still has no idea what words mean. All the vectors are equally far apart from each other. So in this world, the word run is just as different from ran as it is from the word apple. And finally, you've got the out-of-vocabulary problem. If you see a new word that wasn't in your training data, you have no way to represent it.
Now, let's put on our engineer hats for a second and look closer at these vectors. Is this representation really as efficient as it could be? Let's go back to our city example, Mumbai, Delhi, Bangalore. If I tell you a data point is not Mumbai, so the Mumbai bit is 0, and it's not Delhi, so the Delhi bit is 0, what does the Bangalore bit have to be? It has to be 1, right? There's some redundant information baked in here.
This little bit of redundancy leads to a problem with a scary-sounding name, the dummy variable trap. The technical term for the issue is multicollinearity, and it just means one of your features can be perfectly predicted by the others. That Bangalore column is completely determined by the other 2. This can really mess with some statistical models, especially regression models, and make their results hard to trust. The root cause is that the sum of all the bits has to be 1, which means for k categories, you really only have k-1 pieces of independent information. So the solution is beautifully simple. Just drop one of the columns. We can represent k categories using just k-1 columns. And the one we dropped, well, that's now represented by a vector of all zeros.
So here's what that looks like in practice. We just dropped that last column. Mumbai is now 1, 0. Delhi is 0, 1. And Bangalore is now implicitly represented by 0, 0. Boom, we've removed the redundancy and escaped the trap. And the best part for you as a practitioner is that you almost never have to do this by hand. Libraries like Pandas with its getDummies function or scikit-learn's one-hot encoder, they have parameters like drop first equals true that will just handle all of this for you automatically.
Okay, so up until now, we've been focused on how to represent single words or categories. But what if we want to represent an entire document? This brings us to our next big idea, the bag of words model, which is all about counting how many times words show up.
The bag of words model, or BOW, is a real classic in NLP. The core idea is that you represent a document just by the words it contains, and you completely ignore all the grammar, the syntax, and, this is the big one, the word order. The analogy is perfect. Imagine taking a document, literally chopping up all the words and tossing them into a clear plastic bag. You can look in, you can see every word, you can count how many of each word you have, but you've completely lost the original recipe. You have no idea what order they were in.
And the algorithm here is really straightforward. First, you do all your usual text cleanup on your entire collection of documents. Second, you build one single master vocabulary of all the unique words that show up across all of your documents. This vocabulary is what defines the dimensions of your map, your vector space. And then third, for every single document, you create a vector. The length of that vector is the size of your master vocabulary, and each position in the vector is just a count of how many times that word appeared in that particular document. This table, which we call a document term matrix, really makes the idea click. See how each document becomes a row? It's just a vector of word counts. Look at Doc 1. India is a country. Its vector is 1, 1, 0, 0. Just like that, we've turned unstructured sentences into a structured table that a machine can actually analyze. This matrix, which is often gigantic and mostly full of zeros, is the bread and butter input for so many classic machine learning models for tasks like text classification. So what's the final call on bag of words? Well, its big wins that it's simple to get and easy to code up, and it gives you nice fixed-length vectors for your documents, which is what most models need. But the drawbacks are pretty serious. You lose all word order, which means that the sentences, the dog bites the man and the man bites the dog, become the exact same vector, even though they mean totally different things. You also get that huge sparse feature space again. But the most critical problem is that it treats all words as being equally important.
And that brings us to the million-dollar question. Are all words really equally important? I mean, think about a physics paper. Is the word the, which might show up 1,000 times, really as meaningful as the word gravity, which might only show up a few dozen times? Absolutely not. But with simple counting, those common, uninformative words can totally dominate the vectors, drowning out the words that actually carry all the meaning. We need a smarter way to count.
And that sets us up perfectly for the next evolution in our journey, weighing words with TF-IDF. This technique is the direct answer to that problem of everything looking equally important. This is our smarter counting approach.
TF-IDF stands for Term Frequency Inverse Document Frequency. And it's basically just a score that tries to measure how important a word is to a specific document inside a big collection of documents. The best way to think about it is to imagine an expert librarian. That librarian knows a word is probably important to a book if it shows up a whole bunch inside that one book. That's the term frequency part. But they also know a word is really special if that same word almost never shows up in any of the other books in the entire library. That's the inverse document frequency. TF-IDF just combines those two insights into one score.
So let's break it down. Part 1 is term frequency, or TF. This is really just a normalized count. We take the number of times a word appears in a document, and we divide it by the total number of words in that same document. This is just to be fair, you know? It stops longer documents from automatically getting higher scores just because they're long. It measures the local importance of a word inside its own document.
Part 2 is Inverse Document Frequency, or IDF, and this is the secret sauce. This measures the global importance, or how unique and special a word is across the whole collection. We take the log of the total number of documents divided by the number of documents that have our word in them. Now think about a word like the. It's going to be in almost every document, right? So that ratio is going to be close to 1, and the log of 1 is 0.
So super common words get a tiny IDF score, but a rare, specialized word, it will only be in a few documents, giving it a really high IDF score, flagging it as way more informative. Then we just put it all together. The final TF-IDF score is just the TF multiplied by the IDF. So the magic here is that the highest scores go to words that are really frequent in one specific document, but are really rare everywhere else. This is an incredibly powerful way to automatically pick out the keywords that define what a document is about, and it transforms our simple count matrix into an intelligently weighted feature matrix. So TF-IDF is a huge step up from bag of words, because it cleverly weighs words by how important they are. It's an absolute workhorse in things like information retrieval. It's basically the foundation of how search engines rank pages. It's also fantastic for pulling out keywords and for topic modeling. But, and this is a big but, you have to remember it is still a bag of words approach at its heart. It still throws away all word order and context, and it still doesn't understand semantics or what words actually mean. It gives us term importance, but not term meaning. It has no idea that the words king and queen are related, for example. And that brings us to our final section, where we take everything we've learned and make it practical. We're going to build an engineer's decision matrix, a guide to help you make the right call on your own projects. Okay, this right here is the main takeaway for the whole explainer. Think of it as your cheat sheet. Let's walk through it. Use label encoding only when your data is truly ordinal, like small, medium, large. For anything else that's nominal, like city names, use one-hot encoding. But just be careful. It's best for features that only have a handful of categories. Otherwise, your vectors get huge. Now, when you need to represent whole documents for a simple classification task, bag of words is a fantastic place to start. But if you need to account for how important different words are, which is almost always a good idea, you should definitely level up to TF-IDF. It is the better choice for keyword extraction, for search, and for most document classification tasks. The point is, there's no single best method. It's all about picking the right tool for the job. At the end of the day, this whole quest we've been on really boils down to this one idea. The goal is always to transform our text into a format that a machine can actually work with. This language of numbers and vectors, while trying our absolute best to hold on to as much of the original, nuanced human meaning as we possibly can. It's this constant balancing act between what's readable for a machine and what's true to the original language. And that leaves us with one last big question to think about. We've done it. We've turned words into numbers. But every single technique we've talked about today, label encoding, OHE, bag of words, TF-IDF, they all treat words as these separate, isolated things. They can't capture the deep semantic meaning, the relationships between words. They don't know that king is to man as queen is to woman. So the question that should be on your mind now is, how do we do that? How do we create vectors that actually understand meaning? Well, that question leads you straight to the next frontier. Distributed representations, and word embeddings like Word2Vec and Glove. But that is a story for another explainer. Thanks so much for joining me.